Okay. Any questions from last time or earlier? Uh, just as a recap, last time we talked about uh, minimax rates, or rather trying to estimate or learn some properties of distributions. And in particular, what we call the minimax risk was how well does the best estimator learn a property in expectation for the worst distribution, according to some sort of loss function which we might be interested in. And we talked about kind of mean estimation, just kind of low dimensional means or high dimensional means. In each of these cases, we can kind of reduce to hypothesis testing and then prove the lower bound. And also we saw an upper bound, which in both these cases was just that you get a bunch of samples, you take their average and call that your estimate for the mean. Today I want to discuss maybe a slightly different example, which is, I mean, still kind of a mean estimation problem, but with some other restrictions. And I want to show that the upper bound, or sometimes the estimator, can be more interesting, and also the analysis is kind of illustrates a couple of nice techniques. So I posed this as a question last time. Suppose we are trying to look at a collection of distributions, and the property we are trying to learn is the mean. Let's say they're all Gaussian distributions. The covariance is identity. And the mean is kind of from a special family in the sense that it has exactly one non-zero coordinate. Last time I said at most one, but I'll restrict to this case. You can extend the analysis rather easily to the more general stuff. Okay, so let's say they have exactly one non-zero coordinate. I give you a distribution and samples from it, and the goal is to find an estimator or for this mean. Any suggestions of what we can do? Okay, so let's first proceed to see what we can compute just based on samples. Of course, we can compute the empirical mean or just kind of the average, which is what we did last time. And let me call it eta. Just I'm not using mu hat because just as a suggestion that our actual estimator is going to be different. But eta is not a good candidate for the kind of mean we want, because it might have non-zero coordinates everywhere. It's just an average of a bunch of samples. These samples are sampled from Gaussians. Even if the mean is zero, doesn't mean that the entries will be zero in other coordinates. So this can have non-zero coordinates everywhere. And can you suggest how we might be able to maybe look at this empirical mean? Is there something, some way we can process it to figure out sparse mean? Any suggestions?
You can threshold, meaning if xi is small, then you just throw it away.
We can threshold it. So if you mean eta I is small, or the entries of the eta are small, you zero them out?
Yes.
Mm-hmm. So yeah, okay, just notation wise, I'm using I for an index which goes from 1 to n, and I'm going to use j for the coordinates. There are n samples, and each of these samples is d-dimensional. So we have indices both kind of within samples and over samples. So I'm going to use j for the coordinates. And yeah, so in particular, we can try to throw out all the small coordinates of eta. But one issue is that we don't quite know where to set the threshold kind of as an absolute value, because we don't quite know how large the entries of the true mean are. We just know that there is one non-zero entry. So one possible thing could be that we just kind of pick mu hat to be the largest entry of eta. So if and if there are more than one entries which are equal in absolute values, just break ties arbitrarily. So just pick one as your largest entry. We have a budget of one coordinate which we can output as the non-zero coordinate of the mean, and zero otherwise. And we'll see that this can also be written in a different way, which is also a canonical way of thinking about it. And we will analyze this, but this object itself will be a little trickier to analyze, just because there is this sort of thresholding operation which is not so nice in terms of calculating expectations, etc. So before we try to calculate the error, we'll just record a couple of properties of the empirical mean, which is what we will actually use in the analysis. And just note that the empirical mean minus the true mean is just an average of a bunch of Gaussian random variables. Right? It's 1 over n times xi minus mu, the jth coordinate of this, right, over n independent samples. Each sample is nothing but a Gaussian random variable with mean 0, variance 1. We are taking, so when you add independent Gaussian random variables, the variance is add and you still get a Gaussian random variable. This is a property which is quite useful, although we are not proving it here. And so because you have a 1 over n sitting in front, you will get 1 over n square times the sum of the variances. The sum of the variances will be n, so you will get the mean will still say 0, and the variance will be 1 over n squared times n, which is 1 over n. Okay. And using this, we can get a fairly strong concentration bound that the empirical mean has roughly the same kind of entries as the true mean. So for every coordinate j, the jth entry of the empirical mean and the jth entry of the true mean, mu sub j.
Sorry, Madhur, can I ask you a quick question?
Absolutely.
Wait, so this notation is like bold mu j. That's the empirical estimator, which is just the sample mean.
Eta is the empirical, eta is the sample mean or the empirical mean. It's not the estimator. The estimator is mu hat. So let me clarify the notation. Okay. This is our estimator.
Oh, okay.
Okay. This is just the empirical mean or the sample mean. The sample mean itself cannot be used as an estimator because it might have many non-zero coordinates, and we are allowed at most one non-zero coordinate, or exactly one. Okay. And mu is the true mean. So we are getting samples, each xi is coming from the distribution with mean mu and covariance identity. Okay. So there is the true mean, there is the sample mean, and then there is estimator, which is basically the sample mean, but all but one coordinates deleted. Okay. Is that okay?
Thanks.
Good. So, and this kind of deleted object or the estimator is hard to argue about precisely because of these deletions. So most of our argument will actually be about the sample mean and the true mean, and then we'll just sort of talk about the estimator later. And right now what I'm saying is that if you look at the difference of the sample mean and the true mean, every coordinate is a Gaussian random variable with mean 0, variance 1 over n. And because of this, it has a very strong concentration bound. The probability that a single coordinate or a single Gaussian deviates by about by about t from its mean, if the variance of the Gaussian is sigma square, you get this kind of bound with sort of the n replaced by sigma square. And then there are d Gaussians we are talking about. Each coordinate is a Gaussian, and we are taking a union bound over all coordinates. So the probability that any coordinate deviates by at most t, or by at least t, sorry, is at most this quantity, which is d times some exponential in n times t square. This is just the Gaussians of tail bound for Gaussians. So you can estimate the integral once you know the Gaussian density, and you can calculate that the integral above D can be bounded by this quantity. And this is a union bound over D coordinates. Right? So this we're going to use. Any questions before we proceed with this? All right. Now let's get back to our estimator, which we wrote this way. We pick the largest coordinate of eta, tie is broken arbitrarily. And you can also view this as sort of a least squares estimator. So you have your samples, you're trying to find a centroid or some mean for the samples, or you're trying to minimize the least square distance of all the samples from some point mu hat, except that you restrict your mu hat to be sparse. You can check that this is equal to the estimator we have. And also another thing to check is that this equals the true sample mean without the constraint that the estimator is sparse. So these are the things we used last time. So you just try to minimize the least square error. If you minimize it without any constraint, you get the empirical mean or the sample mean. If you minimize it with this constraint, you get the estimator that we wrote down. And in general, you can analyze sort of the least square optimizers under various kinds of constraints and prove things about them. These are just specific examples. And now let's, I claim that I don't yet know the expectation of the sort of square loss or the distance between mu minus mu hat, but I know at least the fact that the distance between the two is not very large, or the probability that the distance is large is relatively small. And the way we prove it is kind of a slight case analysis. So there are two possibilities. We look at this estimator mu hat, right, which we also wrote down here. And both the true mean and our estimator, both of them have exactly one non-zero coordinate. So there are two cases. Either the non-zero coordinates match. Let's say the non-zero coordinate in the true mean is mu1, okay, or is the first coordinate. Without loss of generality, you can just change the analysis accordingly if it's anything else. Okay. And now the two cases are either mu hat also has the first coordinate as non-zero, or it has some other coordinate as non-zero. Okay. Suppose it's the first coordinate which is non-zero, then the 2 norm is just the difference of the two coordinates. And the coordinate which is non-zero is actually just copied from the sample mean. So we are just saying that what is the chance that the sample mean and the true mean deviate? And we already know that this is upper bounded by sort of e to the minus n times t square over 2. So we don't even need this 18. This case is bounded for sure. Now let's look at what happens if we did not find the right coordinate. So the non-zero coordinate in the estimator mu hat is something different from 1. It's not the right one. And let's say it's j for some j not equals 1. Now it's a relatively sort of simple argument. You just have to kind of observe that the way this happens is, first of all, instead of writing the 2 norm, there are only 2 non-zero entries in this vector mu minus mu hat. There is at most 1 non-zero entry in mu and at most 1 in mu hat, or exactly 1, I guess. So instead of writing the 2 norm, I can write down the sum of the 2 entries, just because if square root of a square plus b square is large, then a plus b is also large for non-negative a, b. And or rather, right, because the 2 non-zero entries in mu minus mu hat in this case will be mu1 and eta j. Now, the only way this could have happened is the first entry of the sample mean kind of decreased a lot than what it should have been, which was mu1. And the jth entry increased a lot, so much so that the jth entry kind of overshot the first entry in the empirical or sample mean. So the value of, or the absolute value of the jth entry was larger than the absolute value of the first entry. By triangle inequality, this can be sort of lower bounded by mu1 minus eta 1, sort of the absolute value of mu1. And so in addition to what we have here, the other thing that must have happened is the absolute value of eta j is greater than equal to value of mu1 minus eta 1. Now, if I just add these two inequalities, I get that mu1 minus eta 1 plus 2 times eta j minus 0 is greater than equal to t. Eta j minus 0 is the same as eta j minus mu j, because we are assuming that the only non-zero coordinate in mu was the first one. So you have a sum of two numbers, or sort of a plus 2 times b is greater than equal to t. So at least one of these things must be bigger than t over 3. So but we know that any coordinate can be can deviate from the empirical mean by a factor of t with at most some probability, which is written here. And now we are saying that the only way the 2 norm can be larger than t is if at least one of the coordinates deviates from the empirical mean by at least t over 3. So just apply the previous bound with t over 3 instead of t, and we get this. Okay. Any questions about this part? This is the most complicated part of the proof. Everything else is very simple. It's just a case analysis. The only way the 2 norm of the estimator and true mean is large is if kind of at least one of the coordinates deviates significantly of the sample mean deviates from the true mean. Okay. Once we have this, again, there is I'm writing it out slightly differently. Instead of saying the 2 norm of mu minus mu hat is large, I'm saying the 2 norm square of mu minus mu hat is large. It's just replacing t square by s, just a change of variable. But this is a generic argument that if you're calculating the expectation of a non-negative random variable, in many cases, it's easier to directly prove a tail bound on that non-negative random variable, or just kind of prove that it doesn't grow too large with a very high probability. And tail bounds imply bounds on expectations, although it might be more convenient to kind of compute them through tail bounds rather than just write down the expectations, split it open, use linearity or anything. So that's a generic argument, and here we'll use this. So this is just another formula for the expectation, that you can write it as the integral over probabilities of the cumulative density function. So what's the probability that it's greater than equal to s, integral over all s. This is the expectation in general for any non-negative random variable. Okay. You can check. This is just a simple manipulation of the definition of expectation. Okay. Once we have this, we can just kind of use our tail bound. So let's say we break this integral into 2 parts, from 0 to u. And from u to infinity. Okay, and again, this is generic. I'm not using any problem specific things. Usually you kind of break it or split it at a point where the tail bound starts becoming interesting. So, and now let's just take, so below u, we will just use a trivial bound for the probability. Any probability is upper bounded by 1. And here we will use our tail bound that this is less than equal to 2d times e to the minus. So now I would have obtained n times s divided by 18, but I know that s is at least u, so I'm upper bounding it by, I guess, maybe let me write it. Okay. With these, I can just get an upper bound on these integrals. The first integral is less than equal to u. And the second is upper bounded by 2d times e to the minus n times u divided by 18. And as an exercise, check for an appropriate value of u. So you can use u to be about log d over n and some constant times log d over n, which will give the bound. So it's a slightly more interesting setup where we first proved a tail bound and then used it to bound the expectation. This is, and also this kind of bound is true not just for kind of one sparse means, but in general for sparse mean estimation. Like when you have k sparse, instead of log d, you get k times log d, or rather k times log d over k if you really want to be precise. But and now let's get back to lower bounds, which is the part where we were actually using information theory. The upper bound just illustrates a couple of nice calculating tricks. Okay, so going back to the lower bound, as we said last time, it just basically reduces to proving some sort of a packing lemma. We want to now find a collection of potential means or collection of distributions such that they are at least somewhat far, so they are at least delta far, and at the same time they're not too far. So because the KL divergence is something, I guess, like 1 over 2 ln2 times mu v1 minus mu v2, as we proved, or as I assigned as an exercise last time. Okay, so, but now the additional constraint in our packing lemma is that we want a bunch of points which are one sparse, or which don't have more than one non-zero coordinate. Can you suggest a collection of points which have maybe exactly one non-zero coordinate and are mutually somewhat far from each other, or a distance about 2 delta or between 2 delta and something else? Okay, so let me claim that we can find points, or at least d points in d dimensions. Okay, I'm not trying to find too many now. Last time we found 2 to the d, but there we didn't have any sparsity conditions. Okay, now any suggestions? Okay, the packing here is very simple. The coordinate vectors work. So let's say we look at root 2 delta times E1, root 2 delta times E2, root 2 delta times E sub d, where E1 to E sub d are the coordinate vectors. So E sub j has 1 in the jth coordinate and 0 everywhere else. These are d of them, every pair has a distance exactly 2 times delta. It's kind of square root 2 in the 2 that comes from the L2 norm. So then we get that this is greater than equal to delta square times 1 minus n times, again, we will get some constant times delta square now divided by log d, and is greater than equal to some other constant times log d over n for delta equals for delta, which is again some constant times log d over n square root. So the packing lemma turns out to be quite simple in this case, but it proves that the bound it proves is actually sharp. The estimator is somewhat non-trivial for the sparse case. All right. Any questions? Right. So that's pretty much all I'll say about mean estimation or even minimax rate bounds. As I said, this is just a kind of a brief intro to some of the methods, and there are many. It's a full theory. Now, I want to talk about one operation which we have kind of used or sort of discussed fairly often, is that P star, which is the minimizer of the KL divergence when P is kind of varying over some set of distributions pi, and Q is some distribution which we are kind of sampling from or are interested in the distance from. And we've seen that this exponent shows up in the proof of Sanov's theorem. This also showed up in the bounds and hypothesis testing. And I mean, yeah, in general, this comes up in a lot of calculations. And it also has another useful special case. So when Q is uniform, as you saw in homework 1, that the KL divergence is nothing but log of the size of the universe minus the entropy of P. So minimizing the KL divergence or maximizing the entropy over the set pi are the same thing. So finding a maximum entropy distribution, at least for the sort of finite universes or finite spaces script X, is a special case of minimizing the KL divergence. And both of these operations come up in a lot of settings. For the purposes of the rest of the lecture, I will assume that the support of Q is everything. It's supported on the entire space script X. Every probability is non-zero in Q. Just because any P that we are going to talk about will have the support of P contained in the support of Q. Otherwise, the KL divergence will become infinite and the minimization problem is not interesting. So everything we will talk about will live inside the support of Q. So we might as well assume the support of Q is everything. Okay. So this is the setting we'll restrict ourselves to. But yeah, it's without loss of generality. Now this operation kind of behaves very nicely and is called a projection when pi is of a special form. So we saw that when pi is kind of a closure of an open set or something, a closure of an interior or even a bounded closed set, then we can find or the sort of P star exists, and because if we have a limit converging to the minimum or the infimum, then the limit of the sequence also exists inside the set. And now I claim that in addition, it's unique when your set is convex. So not only does it exist, but is unique. I'll ask you to check this as an exercise. As a hint, use the strict convexity of KL divergence. It's convex in both its arguments, and you can see which one you want to use. All right. So we have a convex set, and we are sort of trying to minimize a strictly convex function on this set. And there I'm claiming that the minimizer is unique, and it exists and is unique. Okay. And we will call this the projection. This is sometimes called I projection or an information projection. I mean, there is also a kind of more generalized operation, but we'll restrict ourselves to this. And we'll denote it by this kind of projection of Q to pi. Any questions about the definition before we proceed? Okay, and in this case, because it's a projection, it has a couple of very nice properties. And so first, there is the algorithmic question of finding this P. I won't talk too much about it. It's in general for convex optimization, when you're trying to minimize a convex function over a convex set, a lot of algorithms that are in the standard toolkit of convex optimization can be used. So I'll not necessarily delve too much into the optimization algorithms. I guess Nathi covers that in his optimization course. Here, I will sort of try to study the properties of the optimizer or the properties of the optimal solution, supposing, I mean, a lot of times it's used as a proof technique, so it doesn't matter that we don't always want to actually find it, but sort of if we find it, we want to study properties of it. And then that's the view we'll be taking in the rest of the lecture. Okay. So it has a couple of nice properties. One, every distribution inside pi its support is contained in the support of P star. So P star is somehow kind of some ways a maximal kind of convex combination, or it sort of doesn't leave out any element which is in the support of any P anywhere in pi. Okay. And the second is sort of like a reverse triangle inequality, but this makes a little more sense when instead of thinking of the divergence of P and Q as a distance, you think of it as a square of a distance, or roughly as the analog of the L2 norm squared. And then it's sort of saying that the angle formed at P star is an obtuse angle. And I mean, the same inequality is also true when you replace the divergence by L2 distance square. And I guess sort of the same proof. But it's a useful property to know about kind of projections to convex sets in general. And the proof is actually, yeah, not very complicated. The basic idea is that if you look at the inequality and kind of look at this function divergence of P with respect to Q, if you sort of follow this function on the line connecting P and P star, or sort of P star and P, then first of all, P star is kind of, the value is lower than every point on this line. In fact, every point in the set pi, because P star is defined to be the minimizer. And it's a convex function. So it's sort of it's a convex function which is kind of growing as you go from P star towards P. And so in some sense, the worst case for this inequality is when it's acting, when P is really, really close to P star. At that point, because we want to prove a lower bound on divergence of P and Q. So the farther you go, the quantity becomes larger and larger. In fact, because it's convex, even the rate of increase is increasing. So it becomes easier and easier to prove the inequality. Just very close to P is the kind of region where we need to be more careful. And the way you capture it is by looking at the derivative. So because of the graph I drew, you can see that the derivative should be non-negative. You can also see it by kind of writing the limit version of the derivative. So first, derivative with respect to what? So let's just kind of look at the line joining P star and P, and let's look at a point P sub t on this line, which is just kind of defined as a convex combination of P star and P. As t approaches 0, this becomes P star. As t approaches 1, it becomes P. And you can think of it as some sort of limit where it's a one-sided limit because we are only sort of approaching t from above. We're not saying anything about negative t yet. But you can think of it as the KL divergence of P sub t, Q, minus the divergence of P star, Q, divided by T. Okay. I mean, yeah, because it's a one-sided, you can make it more precise by just kind of saying, by using the mean value theorem and saying that the derivative is equal to, for any interval, derivative is realized at some point in the interval, but basically this expression, because the numerator is always non-negative, you get that the derivative is greater than or equal to 0. So the function is actually increasing. And another thing is to sort of, just then the rest of the properties just follow by looking at the derivative and just staring at the expression. So I'll leave it as an exercise to check that the derivative with respect to t the derivative with respect to t looks like this. It's p of x minus p star of x times log of p sub t divided by q. Basically just open up the expression and differentiate. So I'll leave that as an exercise.
Can I ask a question?
Yeah, absolutely.
Yeah, what is the support of p or p star? Because I thought it's just a point in the set, right?
P star and p are both points in the set, but p and p star. So this set lives in kind of a real vector space, because there is a number for every probability. So p and p star are both vectors in this space of r to the size of x, the size of script x. And so here I have KL divergence, which is a function on two vector valued inputs. And I'm just kind of parameterizing the input by this single scalar parameter t and just calculating derivative with respect to t. Does that make sense?
No, I'm talking about like above this inequality, there's the support of p, or
oh, I see. Okay. Support of p is just the elements where the probability is non-zero. Okay. So p is a probability distribution. So it has, if the size of script x is r, then it has r numbers, which are probabilities of each of the elements of the universe. And the support of p is just those elements for which the probability is non-zero. Probabilities are greater than or equal to 0, so non-zero just means greater than 0. Does that make sense?
oh, I see. Because I was thinking that p is like a point in this set. But you're talking about the like on the
P is a
edge.
point in this space, but it has
I see.
non-zero, few sort of non-negative coordinates, and we are just now studying which are the coordinates where it's actually non-zero. That's
Okay,
the
got it.
Any other questions?
Are you giving to us this support as a fact, or are we asked to prove this?
We are proving it. So right now, I mean, I stated the claim I want to prove, but I haven't proved it yet. Okay. I'm claiming that by sort of, I guess I kind of gave the derivative intuition for proving the second property, but both of them follow just from the form of the derivative. We'll prove it in a minute, but I haven't proved it yet. Okay. Right, so let's prove it. So we know the form of the derivative. And now the properties kind of just follow from staring at it more or less. So first, recall that we wanted to prove that the support of any p inside pi is contained in the support of p star. So now suppose not. So suppose there is some x where the probability according to p is greater than 0, but it's not in the support of p star, which means the p star of x is equal to 0. Okay. Then for such for such an x, we look at the contribution to the derivative. The coefficient will be positive. It will be p of x minus p star of x, which will be some positive number. And the thing inside the log is tending to minus infinity, because the numerator is tending to 0. The denominator is some positive number. We assume that the support of q is everything. So q of x is always a positive number for every x. So, right, so this is greater than 0, and this is kind of tending to 0. So this term in the derivative is tending to negative infinity, but we said that the derivative was non-negative or was greater than or equal to 0. So we can't have negative infinity. So this contradicts So this can't happen. So which implies that if P of X is greater than 0, then P star of X must also be greater than 0. In fact, yeah. All right, good. The next okay. The next property also just follows by looking at the derivative. So just kind of rearranging the derivative. So we split these two terms apart. The second term can just be written as the KL divergence of P star in Q. And the first term, after a bit of manipulation, you can write it as so we want the KL divergence of P and Q in the inequality that we are trying to prove. So we just multiply and divide by P of X. P of X is non-negative for any X where P star of X is non-negative. So, the other way around, but yeah, sorry, it doesn't matter for this inequality. The thing in front is P of X. So if it's 0, the whole thing is 0. It doesn't matter. And then we can just kind of split it as P of X log P of X divided by Q of X minus P of X log P of X divided by P star of X minus what we already wrote as the KL divergence of P star and Q. And this is nothing but KL divergence of P and Q, KL divergence of P and P star, KL divergence of P star and Q, and we already claimed that the derivative was not negative. So that's the inequality that we wanted to prove. Right, just as an example, let's do a sanity check. Okay, so here's, I guess, a one-dimensional example. So the set of probability distributions is just a subset of this sort of red line, or rather the part which is shaded green. It's a convex subset of this red line, kind of my scribbles notwithstanding. So the red line is a set of all distributions over 2 points over script x, which is 0 or 1. Just it's the line which satisfies P of 0 plus P of 1 is equal to 1. And we are only interested in pi where the probability of 1 is at most half. Okay. And let's take Q to be a distribution where the probability of 1 is 3/4. So the Q is in particular outside pi. And now we are trying to compute the minimizer. Okay. Also, we are trying to compute P which minimizes the divergence of P and Q, where P is now, we are looking for P inside pi, or trying to find this P star. So I've done half the calculation. So I kind of wrote down the expression. Suppose any distribution P can be just uniquely identified by the probability of 1, because the other probability is 1 minus P. And so I've kind of computed the KL divergence of P and Q in terms of this parameter P, the parameter little p. And now the question is, what is P star, or what is the value of little p which minimizes this expression? So the question is, how do we minimize this? Over pi, where pi is just identified by the distributions where little p is less than or equal to half. Any guesses?
You just want to maximize over P. So
Sorry?
you want to maximize over P, or the entropy over P in this case. So
Well, there is this other term also, right? This P log 3.
oh, sure.
Does it matter, the other term?
I think the signs mean that it's still fine.
Yeah, so
Ground.
whatever you are subtracting from 2, both of them are increasing functions of p over p, at least for p between 0 and half. Both these functions are increasing. So you can kind of take p as large as you want, and it will maximize both of these terms, or you will subtract a larger and larger number. So the whole thing is kind of minimized, or the negative terms are maximized at p equals half. And then your p star is just the distribution which assigns probabilities half to each point, or rather. Okay. Couple of things here. Kind of p star lies on the boundary of this set and is something which also minimizes the L2 distance, or the distance from Q. Both of these are not necessarily always true, and this is something we'll see in a minute, some other examples. But just check that over this set, you can show that the inequality is strict. It's the greater than equal to can actually be a greater than. So find a p inside this set in pi, which shows that this inequality is strict. That I will leave as an exercise. Okay. Any questions about the example? Okay. Now let's further specialize. So instead of looking at convex sets or projections onto convex sets, let's look at projections over a very special class of distributions. And these have kind of even further nice properties, which are often used in applications. And this is kind of a family of distributions, which we will call linear families. Okay. And as you would guess, these are defined by linear conditions or linear constraints, in particular by equalities. So you're given a collection of functions, f1 to f sub k, over this space of values script x, or the universe script x, let's say real valued functions, and some numbers, alpha 1 to alpha sub k. Okay. And the family is the collection of all distributions such that you fix the expectation of each of these functions. So you're saying, I'm willing to accept any distribution such that the expectation of fi is alpha I for each of these i's. And this defines a collection of distributions. Okay. In general, I mean, fi could be x square, and so this is saying that the second moment is something, or it could be x cube, and it's saying the third moment is something. So anytime you specify a distribution or a collection of distributions by fixing the moment, it looks like this. And a lot of times kind of this is how we study distributions. We kind of estimate some moments, and then we try to figure out what class of distributions are consistent with the moments that we calculated or estimated. And these are, in general, these will be linear families. Okay. Any questions about the definition? So you can also define them over infinite universes script x. Right now, I kind of was looking at the finite universe case, but the nice thing about KL divergence is that because the KL divergence is kind of supremum over sort of finite partitions of any universe, you can essentially take all the theory from the finite case and lift it to the infinite case with some care, just kind of making sure things exist and so on. But let's say we want to look at collections of all distributions such that certain expectations are fixed for f1 to fk, and these could be arbitrary functions, not just moments, but moments are a special case. And here I claim that the under certain mild conditions on this linear family, which I'll state in a minute, the inequality is actually strict, and you get like a Pythagoras-like theorem. So if again, instead of the divergence, you think of the square L2 norm, then you are saying that if you think of this family as a subspace, then you're kind of saying that the distance of between p to q whole squared is equal to the distance between p and p star whole squared, and the distance between p star and q whole squared. This is what happens when you kind of look at a projection onto a space over L2 distance, and if you were thinking of the projection under L2 norm of and again, KL divergence is not symmetric. It's not a true distance. So this picture is only for intuition. It's not kind of a formal equivalence. Okay? It's just an intuitive way to think about it. Any questions? All right. So let's prove this fact for linear families. And the additional condition which I said we need, here I will just kind of assume that inside this linear family, no element is left out. So at least there is some distribution which has some positive probability for that element. Okay? So can't happen that everything in this linear family doesn't assign any positive probability to x1, or sort of x1 just never occurs. Okay? So this is the kind of case, because then yeah, Q, the support of Q is everything. And so like if you are never allowed to put weight on one of the elements of Q, then so the expressions can look a little weird, but this is usually a mild condition. Under this, we can prove the property that we wanted. And in particular, I'll actually show two things. One, that P star is also kind of in the inside of this set, this collection of distributions L, or which is now our pi. The collection of distributions is this family L, and it's on the inside in the sense that for any P inside in this set, if I can look at the line connecting P and P star, this line is certainly contained because the set is convex, but I can also move at least a little bit in the other direction. I can go kind of overshoot a little bit and go beyond P star on the same line, and at least for some amount beta I can keep going. So there are points on the other side, sort of in whatever direction I look at. The way it's defined this way, or it's called the relative interior, is because it's not that you have a ball contained in the set. This set is defined by the intersection of a bunch of hyperplanes, these linear conditions. So the only movement you can have is on all those hyperplanes. So you can only move in a direction which is allowed by other points inside the set. So this is the way of capturing that. There could be other equivalents. Before, the proof is going to look at the derivative, but before we go there, let's just see what can prevent us from kind of moving in the other direction on this line. So for this distribution P sub t to be in the set, two things have to happen. It has to satisfy all the linear equalities, and it has to be a distribution, or the probabilities have to be non-negative. The fact that it satisfies all the equalities is actually very simple, because we can just write this, or we can just split the summation, and the equalities are true for P star and they are true for P. Doesn't matter if T is positive, negative, whatever value, you're just kind of adding these two, and so you get alpha I. So the equalities are always satisfied. There's nothing kind of off there. The only issue is that the probabilities might become non-negative, or so the probabilities might become negative. They might not remain non-negative if you kind of move in the other direction. But in particular, we know that the support of P star contains the support of any P inside this set. We just proved that a couple of slides ago. So, so in particular, and in fact, we proved this for all P inside our set. The union of their supports is everything. So the support of P star is actually also equal to everything. We don't need that strong a property here, but it's fine. It's easier to argue it with this. Now, so every probability is positive in P star. So each is some number, say 0.1. If it's 0.1, we can at least move it a little bit in the other direction before the kind of smallest number, which is appearing in the probability distribution, goes down. So we can at least move for beta, which is smaller than, let's say, the smallest value in P star divided by, this is how much kind of taking negative t would decrease the value. It would decrease it by, the t would multiply p minus P star. So if you take t to be 0.1, it will sort of decrease P star of x by 0.1 times P of x minus P star of x. Again, it's a simple check, but there is some positive beta that I can take such that I can at least take t to be up to beta. But now if I can take it at least somewhat on the other side in the line, then this P star actually should not just have the derivative greater than equal to 0, it should have the derivative equal to 0 because it's a minimizer in both directions. And the reason this equality failed, as we just saw in the example, was because our P star was lying on the boundary. So we couldn't move in the other direction. And so the derivative was greater than equal to 0, but not necessarily equal to 0. But now it's inside, so we can actually move in both directions, and the derivative is exactly equal to 0. And that gives us the equality we wanted. Any questions? All right. Okay, let's continue, and maybe let me mention a related kind of class of families which comes up when you try to talk about linear families. So when you want to talk of what are the distributions where the expectation of x square is something, or fix some moments. In general, when you try to fix a bunch of moments and say, what is the maximum entropy distribution under these conditions? It turns out to be of this form, which is what we call an exponential family. And in general, what we'll show in a minute is that the minimizer or P star, when we are trying to minimize over a linear family, the answer turns out to be in an exponential family, or it looks of this form. Okay. So what is an exponential family, first of all? It's defined by some kind of reference distribution Q and some functions G1 to G sub K. And the family of distributions is all the distributions such that there exist lambda 1 to lambda sub k which satisfy this property. That for all x, P of x is equal to some scaling of Q of x. And the way it's scaled is actually just depending on the values of these functions G sub x. Most cases, you can think of Q as uniform, let's say, to start with. So Q of x is always 1 over the size of the space. And then you're just saying the probability actually only depends on G1 of the value of G1 of x, the value of G2 of x, and so on. Okay. So, and it turns out that this will be true when we are trying to kind of compute the projection. So it's kind of a nice theorem that's saying that if you want to look at all distributions where the expectation of x square is some number alpha, then the distribution will look of the following form. The probability of an element will be just e to something times the value of x squared for that x. Okay. So if you want a distribution which maintains expectations of certain functions, and if you're trying to minimize the KL divergence, then this distribution is something which actually only depends on the value of these functions. It's the same functions that show up. So the G1 to GK will be equal to F1 to Fk. And so, for example, probably heard the fact that the maximum entropy distribution subject to moment conditions when you fix the first and second moments is a Gaussian distribution. And there the probability is kind of replaced by probability density and so on, but the Gaussian probability density is something like e to the minus x minus mu sigma squared. So what we are saying is that we are trying to look for a distribution where the expectation of x minus mu square is equal to something, and the distribution turns out to be something where the probability just depends on the value of x minus mu square. Okay? So just whatever quantity is the one that you care about in expectation, that's the one the probabilities depend on, nothing else. I mean, up to this factor of q in front, which is the distribution you were planning to start with anyway in terms of minimizing q divergence. Any questions about the definition or the statement? We'll prove this in a minute. Okay. So exponential families have sort of lots of applications, particularly in kind of graphical models and sort of maximum likelihood estimation, etc. There is this very nice monograph of Michael Jordan and Martin Wainwright. Take a look at it if you are interested in these kind of topics. Here we are just kind of giving them as an example, but they're a nice family of distributions and show up in a lot of applications. I'll actually prove this for the case of k equals 1, where you care about the expectation of one function. The proof is essentially identical when you're looking at more functions. So let me just do this. The idea is the same. And we are trying to minimize, so let's write down explicitly that we are trying to minimize the KL divergence of P and Q over this linear family. And now let's write down this linear family as a bunch of linear conditions. So we are trying to minimize a function which is convex in P. P's are variable, and these are linear inequalities in P. Okay. So in particular, and as I said earlier, minimizing a convex function over a convex set is something which we understand relatively nicely. So we can compute this, but again, here we are more interested in the properties of the minimizer, what it looks like. And the way to do this, or one way to do this at least, is to look at this minimizer through the lens of convex duality. So let's write down the minimization problem in a somewhat more complicated way. So let's make our life harder. So let's do that. And instead of saying that I'm going to minimize this function subject to these conditions, I'm going to say that I will just not enforce these conditions as hard constraints, but just sort of introduce penalty terms. So I will write down lambda 0 times how much the condition of summation p of x equals 1 is violated by, lambda 1 times the other condition. And I will write down this expression, which is sometimes called the Lagrangian form. So which is the quantity we wanted to minimize in the first place, plus the other constraints now replaced by these penalty terms. Okay. And I claim that the minimization problem we are solving can be written, again, in a more complicated looking form in this way, that we're trying to compute the minimum or the infimum over P of the supremum over lambda of this quantity that we wrote down. Okay. And that's just because, at least the way we wrote it down, the inside is actually equal to infinity if summation p of x is not equal to 1, or summation p of x f of x is not equal to alpha. Because let's say we're kind of solving this problem as a two-player game. So my goal is to choose a p, and such that no matter what lambdas you choose, this quantity is not too large. But if I chose a p where summation p of x was not equal to 1, you will just choose lambda 0 to be infinity or minus infinity depending on the sign of that term, and the quantity will tend to infinity. So I have no hope if I didn't satisfy these two conditions. So if the quantity is bounded, then the only way this can work is actually it satisfies these conditions. Okay, this is not a formal argument, but it's mostly there. And it can be lower bounded by something which looks similar, but I've kind of switched the infimum and the maximum or the supremum. Which is referred to as the dual program. Now, this is lower bounded because earlier my job was to find a P such that the quantity is minimized no matter what lambda 0, lambda 1 you choose. So I have to kind of anticipate everything you could have done. Now we are changing it. You give me your lambda 0, lambda 1 first, and then my job is to pick the worst P. So my job became a little easier. Your job became a little harder, but I'm a lazy professor. I don't care about it, and that's what exercises are for. So that's something where I can potentially reduce this quantity even more. And that's called the dual program. The nice thing is that actually your job did not become too difficult. So sort of equality holds. Under kind of relatively benign conditions. And this is called strong duality. Just the inequality itself is referred to as weak duality. And here it will hold under the condition that kind of there exists some P inside my family such that P of X is greater than 0 for all X. So in general, this is called like there's some point which is strictly feasible. So all inequalities are strict. This is called Slater's condition. It's a sufficient condition. It's not necessary. There are other sufficient conditions, but this one is relatively clean, and we can work with this. Okay. In particular, we did talk about our P star and said that our P star sort of satisfies this property that P star of X is greater than 0 for all X. So under this condition, the two programs are equal, but now it kind of makes my job much easier. So instead of trying to come up with P or trying to characterize this P, which must be kind of anticipating all lambdas and working against them, my job is now just to say, how would I choose P if I was given lambda 0 and lambda 1, and what would P look like? And this is a much easier problem. In particular, I can fix lambda 0, lambda 1 and kind of minimize some quantity over P. And not worry about these hard conditions, P of X minus 1 or P of X, F of X minus alpha, sorry. Because, again, we got rid of these hard conditions by introducing penalty terms, and now my only job is to just minimize the penalty term over P, or like this expression, the Lagrangian over P, given lambda 0, lambda 1. This is not too bad. In particular, I can calculate the derivative. You can check that the derivative comes out to be this. Again, it's just simple calculus on the terms above. And if we set the derivative to be 0 at the minimizer, we get a relatively nice condition that log P of X divided by Q of X is equal to minus log 2 ln 2. Let's see. I'm just writing 1 as log 2. Okay. Okay. Let's see. Minus lambda 0 minus lambda 1 times f of x. And so P of x divided by Q of x is equal to 2 to the minus log 2 over ln 2 minus lambda 0 minus lambda 1 times f of x, or rather p of x is equal to q of x times this. So it is of the form that we wanted. It's q of x times some constant maybe times lambda 1 times the function that we care about. And it only depends on up to this factor q of x. It only depends on the value of the function that we care about. That's the derivative for, that's the derivation when you have one function. If you had multiple functions, the only thing that would change is you will have many more terms in this expression, and all of them will go in the exponent, but nothing else will really change in this computation. Okay. And again, if you want an introduction to convex optimization and duality, Boyd and Vandenberg is a standard reference, and in particular chapter 5 is a very good reference on convex duality in case you want to take a look. All right, now let me assign an exercise which is kind of maybe not exactly, well, you can reduce it to a linear family, but let's write down. So if you remember, we in sort of hypothesis testing, we talked about this setup. Where we were looking at P and Q, or sort of we're looking at sets of this form. This. It doesn't matter, something on the right hand side. And we were interested in sort of computing argmin of P and pi and KL divergence of I forget if it was P0 or P1, let's say P0. Either pi or pi complement with P or P1 or P0, right? So that I will assign as an exercise. So just based on this, we kind of wrote down some form of for this one, that it looks like P0 to some power, P1 to some power, normal divided by some denominator. So check that the minimizer so this is something, I mean, the denominator, so that the whole thing sums up to 1. Okay, I'll stop here. This particular form of the exponential family has lots of applications. As we saw, it already, because we kind of think of maximizing entropy as minimizing KL divergence, we already proved that the maximum entropy distributions subject to some kind of linear conditions always look like some sort of exponential family, or coming from some exponential family. So in general, this is a characterization of maximum entropy distributions. Another algorithmic applications, we will, maybe I'll talk next time briefly about this question of sort of matrix scaling, which is a special case of operator scaling. And these are things where, I mean, this can be used in getting algorithms for bipartite matching or permanent or something. And it's sort of the more general framework has applications to kind of lots of inequalities in analysis and so on. So I'll maybe briefly mention next time, but just the form of the optimizer, the fact that it looks like belonging to some exponential family often is quite useful in applications. And I'll try to show an example next time. Stop here. Any questions? something that was unclear, too rushed?
Can I ask you to go back to this point about the KL divergence being 0 for
KL divergence being
sorry,
0?
not the derivative of the KL divergence.
This one or the next one?
Next one.
Okay. This one?
Yeah, I'm kind of unclear as to where this conclusion comes from.
Right. So it's kind of the same argument as we used before, that if we are approaching P star from the side of P, we said that the derivative has to be greater than or equal to 0, or the function has to be increasing as we go towards P. And now it also has to be increasing in the opposite direction, because I mean, if we can move in the opposite direction, it has to be increasing. So P star must be a local minimum. And because it's a local minimum, we just set the derivative to 0. It's a local minimum along this line. So in particular, the derivative along this line is equal to 0.
Sure. Yeah. Okay.
So formally, the limit that we defined, now you can define it as a two-sided limit and say that it approaches 0 from both sides. Like it's, yeah, from both sides, you can show that it goes to 0.
But what's the difference between this setting and the previous setting, so that the previous one can, like, you cannot say it's
this part. So in the previous setting, it was possible that P star is on the boundary, so we can only approach P star from one side. So just going back to this picture, if P star was on the boundary, we will know that it kind of increases on the other side, but maybe if we were allowed to cross the boundary, it would decrease even further. It's just that because of the boundary, we cannot move anymore, or we are at the boundary of pi. So P star need not be the local. I mean, it's not the minimum because the function is kind of has a local minima or is derivative 0, but just because we have reached the boundary.
Okay. Okay.
And that actually happened in this example. You can compute the minimum if you are allowed to kind of move a little further from out of the boundary. I mean, yeah, maybe not as far as Q, because otherwise the question will become trivial. But if you move the boundary a little further from half, you can check where the minimum occurs. Might be a good exercise. Any other questions?
I can ask, why is it non-negative if it's like at the boundary? Because it seems like it could be either direction, right? It could be.
Yeah, so it's non-negative because of this expression. So in particular, when I look at any positive t, the KL divergence of P sub t and Q is greater than or equal to the KL divergence of P star and Q, because P star is the minimizer, at least inside pi. And for any positive t, all these points are inside pi because of convexity. So at least for any positive t, I can say that the numerator is greater than or equal to 0. And then I'm taking a limit.
Oh, okay. Let me.
I mean, okay. The more formal way of saying it is really that that the derivative, or rather, if I look at the difference between PT and Q minus the KL divergence is P star and Q, then this distance sort of difference over T is realized as the derivative of the same quantity at some T prime, which is between 0 and T, because of the mean value theorem. And now I push T towards 0, so T prime also gets pushed to 0. And then when T prime is pushed to 0, the right-hand side becomes the derivative.
Okay. And this thing is always at least non-negative.
It's non-negative because P star is the minimizer, at least on this line, right? And P sub T is always on the line.
I guess I'm just wondering, because it seems like, because you were saying the KL divergence is a convex function, and you're definitely optimizing convex set. But like, what's this different? What's the difference between this and some other convex function that you can say that this minimizer you can guarantee t.
So the derivative, so the convex function can be minimized either at an interior point of the convex set or at the boundary.
Yes.
If it's minimized at the interior point, I know the derivative is equal to 0.
Yes. Yes.
If it's at the boundary, I don't know that the derivative is equal to 0. But because I'm kind of minimizing, I still know that if I kind of approach from the side of the convex set, the function will keep decreasing. Right? It
Okay.
can't be like, it can't happen that the minimizer is on the boundary, and as I kind of walk from the minimizer inside the set, the function starts decreasing further, because then that would have been the minimizer wherever it decreased inside the set. The fact that the
Okay.
minimizer is on the boundary means that at least in the neighborhood of the minimizer, the function must be a bit higher. That's why this is the minimizer, at least till the point I hit the boundary.
Okay.
I mean, just sort of think of y equals x squared and trying to kind of minimize it between 1 and 2. So 1 is the minimizer. So that means that the derivative at 1 is greater than equal to 0. In particular, if you kind of walk from 1 towards 2, the function is increasing. But the derivative is not equal to 0 at 1 because it's not clear that on the other direction it's also increasing. If you were actually allowed to go past 1, the function would continue decreasing. It's just that the set doesn't allow us to go there.
Yeah, I like, so for example, why is it not like optimizing over, like, let's say between -2 and -1? Like in that case, you're gonna get like a minimizer with derivative smaller than.
Right, so let's write down that example. You want to minimize between -2 and -1. So let's write down y equals x squared. Sorry for the drawing. Okay. And we want to minimize it here. And this is the minimizer now.
Yeah.
And as I walk from the minimizer to the interior of the set, the function is increasing. Because this is the minimizer. So sort of in the neighborhood, the values must be higher. That is why this is the minimizer, right?
Yeah.
So the derivative, okay, yeah. So here, the derivative is kind of defined on this line, and the parameterization is such that we are looking at p sub t, which is equal to 1 minus t times p star plus t times p. Now, this is our p and this is p star. So as t is increasing, you are actually walking towards p. It's just, don't think of the x-axis as the derivative, as the variable with respect to which you are taking the derivative. You're taking the derivative with respect to t, which is walking in, which is growing in whatever is the direction that is the interior of the set. So here actually -x is the variable t, roughly speaking. And so the derivative is increasing as you kind of increase -x or increase t. T is kind of pointing you towards the interior of the set, right? That's how we define this.
Oh, okay.
It's
I
not,
see. Because it's like you define this direction, so it's you're gonna always get non-negative.
yeah. So the derivative is positive with respect to t or non-negative, and because growing t always pushes you towards the interior of the set. And we know as we walk towards the interior of the set, the function increases.
Okay, got it. Thanks.
Any other questions?